Welcome to The Explainer. Today, we're taking a seriously mind-blowing journey. I mean, we're literally zooming all the way from the microscopic mechanics of optical physics straight into the human body. We're looking at this amazing piece of tech that starts out as just a simple, tiny thread of glass and somehow transforms into a literal life-saving medical sensor. Yup, we're talking about tilted fiber Bragg gratings. Let's get into it.
So, here's our game plan for today. We're going to start with the magic of fiber gratings, then introduce the game-changing tilt, look at dual sensing for both temperature and liquids, how we forge the fiber using phase masks, supercharging these fibers with gold, and finally, real-world medical marvels.
All right, part one, the magic of fiber gratings. Okay, so to really grasp this, I want you to imagine standard fiber Bragg gratings, or FBGs, as this series of tiny, totally invisible mirrors etched right inside the microscopic glass core of an optical fiber. When you shine a light down that fiber, these little mirrors reflect very specific wavelengths of light back to the source, but they let all the rest of the light pass right on through. Now, because these internal mirrors are super sensitive to the glass stretching or heating up, they're fantastic for measuring internal strain or temperature. But, and this is a big but, they have a huge limitation. The protective outer layer of the fiber, which is called the cladding, basically traps all that light inside. So a standard FBG, it is completely blind to the outside world.
Which brings us to section 2, introducing the game-changing tilt.
This is where things get really cool. The contrast here is just fascinating. By taking those microscopic internal mirrors and simply angling them, just tilting them a few degrees to create a tilted fiber Bragg grating, or TFBG, we suddenly allow that trapped light to leak right out of the core and interact with that outer clouding layer. Boom. Just like that, we've turned the outside surface of the fiber into this incredibly powerful sensor that can actually detect non-mechanical stuff happening in its surrounding environment.
And the actual mechanics happening here? Absolutely breathtaking. Because of that tilt we just added, our single stream of light literally splits its duties. Part of the forward-moving light gets excited into what we call backward conducting cladding modes, basically bouncing around that outer layer. Meanwhile, the original backward conducting core mode, that stays perfectly intact. So we're suddenly getting two highly precise sets of data at the exact same time. And the signal is ridiculously sharp. It creates this high-density comb of narrow-band spectral resonances with a massive Q factor of 10 to the fourth power. Which, is really just a super fancy physics way of saying the signal is stable and impossibly precise.
And when you actually look at the transmission spectrum, you can clearly see what I mean by a comb. Look at that massive, dense row of sharp dips. Every single one of those dips is a specific clouding mode resonance. Whenever the environment outside the fiber changes, even just a tiny bit, this entire comb shifts. It acts as an insanely accurate measuring tool.
Moving on to section 3. Dual sensing for temperature and liquids.
All right, so remember how we have those two data streams, the core mode and the cladding modes? Well, in the medical field, you often need to measure the refractive index of a fluid. Think blood or other biological liquids. The problem is the human body's temperature is constantly fluctuating, and that naturally skews your readings. It's a huge headache. But researchers found this brilliant workaround. Check this out. When the temperature changes, say from 293 up to 353 Kelvin, both the core mode and the cladding modes shift linearly. But if the refractive index of the liquid changes, that only shifts the cladding modes. The core mode totally ignores the liquid. So by tracking both modes simultaneously, researchers can just do the math and separate the temperature from the liquid's actual composition. It's a single, microscopic probe giving us two perfectly calibrated measurements at once. How cool is that?
Okay, section 4, forging the fiber with phase masks.
Now, you might be wondering, how do we actually make these things? Historically, crafting them was a total nightmare involving incredibly complex lasers and mirrors. But researchers managed to simplify the whole thing, which is exactly what made them commercially viable for everyday use. First, they stripped the polymer jacket right off a single-mode optical fiber. Then, they blast it with a high-power, pulsed 266-nanometer ND-YAG UV laser. But here's the clever part. They fire this laser through a specially designed piece of silica glass called a phase mask, which creates a highly precise interference pattern. As the UV beam hits the fiber, it naturally refracts, permanently burning that tilted grating straight into the core with unbelievable stability.
If we look at the setup here, you can visualize exactly how this works. The UV laser comes down from the top, passes through that phase mask we just talked about, and refracts right into the fiber optic core.
In one of the major breakthrough experiments for this tech, they actually used an external setup angle of 11 degrees, and once that light refracted through the glass, it resulted in a super precise 7.3-degree tilt, permanently inscribed right inside the core. It's just brilliant engineering.
Which takes us to Section 5, supercharging fibers with gold.
All right, so we have our sensor. It reads temperature, it reads liquid composition perfectly. But what if we want to detect really, really small stuff, like microscopic biological molecules, individual proteins, or even cancer cells? Well, we need to dramatically amp up the sensor's sensitivity. And we do this by wrapping the outside of the fiber in a microscopic jacket of pure gold. Literally pure gold, exactly 15 nanometers thick. Because our grating is tilted, it polarizes the escaping light. That light hits the gold film and excites what are known as surface plasmon resonances. Essentially, adding this tiny, very expensive little jacket supercharges the fiber. It massively amplifies the electromagnetic energy on the surface, which drops our detection limits all the way down to the nanomole or even picomole level. It is a total game changer.
And that brings us to our final stop, Section 6, Real-World Medical Marvels. So it really begs the question, right? How does a single strand of glass, coated in an absolute whisper of gold, actually tell a doctor what's happening inside a patient's cells?
Well, let's look at one specific, truly groundbreaking application, the calmodulin biosensor. Calmodulin is an absolutely critical protein in the human body. It regulates your vital enzymes, controls cell proliferation, it even mediates human memory. And if your calmodulin levels are off, it severely disrupts your metabolism and nerve growth. It's a really big deal. To actually detect this in real time, scientists took one of our gold-coated plasmonic TFBGs and biologically bonded these things called transient receptor potential, or TRP channels, directly to the gold nanofilm. You can think of these TRP channels like little biological catcher's mitts that are perfectly shaped to just grab calmodulin proteins right out of a fluid. The result is real-time, label-free detection of this incredibly vital protein.
And the sheer scale of this achievement, it is mind-blowing. Thanks to that tilted grating combined with the gold plasmonic amplification, this sensor has a limit of detection of 0.44 nanomoles. Think about that. We are measuring critical biological phenomena down to less than half a single nanomole. And we are doing all of this using a device that is roughly 125 micrometers across. I mean, that is literally thinner than a single human hair. And it only requires microliters, tiny, tiny drops of sample fluid to work.
This amazing marriage of fiber optics and plasmonics is entirely redefining what is possible in medical diagnostics. We are rapidly moving toward a future where single-point, in vivo biomedical sensing right inside the hardest-to-reach spaces of the human body is an absolute reality. So, if a single strand of glass can read the vital proteins regulating our memory and cell growth today, I want to leave you with this. What invisible worlds will it reveal tomorrow? Thanks so much for joining me on this explainer, and keep your eyes fixed on the future.